Hello, dear students. In this short video, I would like to show you how we can do a gradation analysis of a toolpath. The gradation analysis of a toolpath. I have considered an example here, and I'm going to show you some of the MATLAB scripts that I wrote. And through those MATLAB scripts, you can perform a gradation analysis. So what do I mean by gradation analysis? Let me first tell you that. Let's say that this is my toolpath. And the material will be deposited along this toolpath. So I'll just create another copy of this toolpath so that I can reuse it. One more copy. Yeah. Okay. So this is the toolpath, and the material is going to be deposited along this toolpath. And you can see that as we go along, let's say that this is my positive x direction. This is my positive x direction, and as we move along the positive x direction, then the amount of material which will be deposited over this region is significantly higher as compared to the amount of material which will be deposited over this region. Of course, I'm making this not very rigorous, but you can see that at least qualitatively that over here the amount of material which will be deposited is significantly lower. You can see because of the step over values, it's going to be significantly lower as compared to this particular region. So then the density here would be lower, and the density of the material deposited over here will be higher. And that's how you create a gradient in the printed part, in the deposited part. However, if I were to do a gradation analysis, then how will I do it? Now, what do I mean by a gradation analysis? So let's say that you start moving from this direction, right? As you start moving along this direction, and I'm going to be moving along, let's say, an axis. I'm going to be moving along an axis like this. So this is how I will traverse. It's a horrible line. It's not straight, but just assume that it was a straight line. So for the first few travel units, I wouldn't have encountered any material. So the density is 0 here. So this is just let me write this as 0. So this density is 0 here. But as soon as I come over this region, because the material would have been deposited here, I will get a density of 1. So I'll get a spike. All right. So all this was 0 density. Then I got a spike. Then I kept moving forward. Again, I got 0 density because there is no material deposited here. Then again, I got a spike because you encountered this toolpath. Then this is all white space, 0 density. Then I come over here to this particular toolpath and I get a spike, then 0, then I get a spike, then 0, get a spike, 0. So throughout this region, the density is 0. Then again I come here, so at this particular location in x-axis, I'll get a spike, and this continues periodically. But then as you come to this extreme right hand side, the number of spikes that I'm going to get is significantly higher as compared to this particular region. So if you were to imagine that it's all zeros and ones, either you are getting no density or you are getting a spike. So you start moving from one direction to the other. You start moving, there is 0 density, but you come on the toolpath where the material would have been deposited, you get a spike. Then again it drops to 0. As soon as you clear that region, clear that spike deposited area, your density drops to 0 and blank, then density up, then blank, then up, a spike, and it continues on. So what I wish here So what I want to do here is I want to create a method to scientifically analyze as to what is the region which captures the gradient in the density. So if I were to say that this is my particular region and I compare it to this particular region, wouldn't you say that the density in this particular region is lower than the density in this particular region? And the reason is you're getting much more frequent spikes here as compared to here. So, but that is the case which is within this domain. So this domain is X and this is Y. And similarly here also this is the same domain. So this is X and then this is Y. However, if I reduce this X and Y domain such that it barely covers one particular toolpath, one particular track of the deposited bead. So now this is my new X1, which is this distance, and this is my my Y. This is my Y1. So this X1 Y1 domain, which is this domain, I apologize, I'm making a bit of a mess. So within this domain, this new domain of X1 and Y1, if I were to take this domain here, here, so that it barely covers just one of these toolpaths. So now you can see, you can say that the density is same in both these two domains, in these two regions. This X1, Y1, the domain which is given by this X1 and Y1, which barely covers one single track, one single toolpath. If I were to take that particular domain, that domain area in the left hand side and in the right hand side, then the densities would be the same. So what is the effect of this domain size on the gradient of the toolpath, on the gradient of the deposited material? So clearly in one case, when you would have taken a domain of X and Y, you would have seen the gradient. However, if you take this X1 and Y1 as your domain, then you will come to the conclusion that there is no gradient over here and over here, on the extreme left and on the extreme right. I hope I'm making sense. So then the question is that, okay, if this is the case, can we write a code in MATLAB that lets me see that as I vary the domain area, what happens to the gradient that I see over the entire toolpath, over the entire deposited region? So for that, I propose this particular methodology. The methodology goes like this. This is an image. Let's say that this is an image of the toolpath. What I'll do is I'll perhaps create a boundary here. Picture boundary. Yeah. So now this black color thing that you're seeing, this is the area which was covered by this particular toolpath. So this is the space. We are not going to talk beyond the space. So we are limiting ourselves to this black color boundary, which I've just created. So we are going to look at this particular boundary, and we are going to look at how the material is deposited in this particular boundary. Now, if I were to take a domain within which I wish to analyze the within which I wish to analyze the gradient. So let me say that this is A and then this is B. So over here, I wish to analyze the gradient. So this A and B is going to be a window, and I will move this window, and I will see the gradient. So what I want to do is this particular image of a toolpath, I will convert it to grayscale. So I'll convert this to grayscale, and I will take this domain. So this has some pixels. So this is pixel and this is pixel. So this is A pixels wide and B pixels tall. So I will take this window, and I will take the pixel intensity values within this window. So within this window, each pixel will have a certain intensity value. Let's say it varies from 0 to let's say 255. If it is 0, it is completely black. If it is 255, it's white. And between 0 and 255, it can have many shades of gray. So from black to white. So each of these pixels, I will take the intensity values of each of these pixels, and I will add them. So add the intensity values. So I will write, let's say that I1 in is particular intensity of a pixel. So let's say this pixel. So I'll sum the pixel intensity values for all n, and I'll divide it by the number of pixels. So the total number of pixels. So I will get a quantity here. Let's say I got the I average. So for this particular window, I got an I average. So let's say that it came around 100. So this is my average intensity value. What I will do with this is I will create another figure. So this is a completely new figure. I will create a new, apologies. So I'll create a new image where within this A cross B, so this was A and this was B. Within this A cross B, I will fill this particular color of the gray. So I will fill this entire block with an intensity value which is 100. So I'll fill this entire thing with a intensity value which is 100. So all of this is now represented by this, right? Okay. Then I'm going to move this window along the positive x. So let's say my window comes over here. So again, within this window, there will be lots of pixels. Each pixel will have its own intensity value. So mostly, as is the case here, mostly what will happen is these pixels will have 0 values, because this will be completely black. I'm going to convert it into a grayscale image. And this line, all the pixels that fall within this toolpath line will have an intensity value of 1. So I will take again the average of all these, and correspondingly I will fill this entire region with whatever, let's say I got 50 as the average pixel intensity by this formula, and I will fill this here. So this is 50. Similarly, I will keep moving this block. Let's say I'm over here. So now you can see that there would be a lot more ones than zeros. So the average pixel intensity would be, let's say I got 200. So the average pixel intensity, I got 200. Again, take all the pixel intensity values within this window, and please keep in mind that I'm keeping the size A and B same. So A width, B height, I'm keeping the same. So all the pixel intensity value within this domain I'll take, and I'll take the average of it, and correspondingly I will make a plot here. So this will be 200. So all the pixels within this new image will have the same intensity values. Okay. Having developed this methodology, the thing that remains to be done is I will vary the domain size, this A and B size. Okay, this A and B size. I will vary this A and B size. I will try to make it shorter, smaller window, and I will try to make it a bigger window. And then I will look at the results as to when I move this, when I play around with this A and B values, what exactly happens to the gradient? What exactly happens here? So as I play around with this A and B, what exactly happens to this new image? And by doing that, I'm hoping to gain some insight into this gradation analysis. All right. So now let's see how to do that. Okay. So now this is the MATLAB code. So this is actually the tool path. So if I were to open this here, you can see that this is the tool path. So this is the tool path. So these are the x coordinates, and then these are the y coordinates. Okay. So here what I'm doing is I'm just simply loading the tool path. So I'll just quickly run this section. And what I will do is I will do a scatter plot. I will do a scatter plot to show you the tool path. Okay. Okay, so this is the tool path. You can see that these are the points. These are the points that will be that the deposition head is going to follow. A better thing would be to just instead of giving a scatter plot, I can just give the plot command and show you. Yeah, so again, this is the toolpath that it's going to follow. So that's what I'm doing here. I'm just loading the x and y coordinates. Then I'm going to export those the picture, the plot window as a JPEG file with a resolution of 300. Let me run this, and okay, so this is the output, and correspondingly after I have run this, you can see that I have created a new file. This is example.jpg. here it says that the width of this image is 1666 pixels and the height is 106 pixels. Next, we come to next. What we need to do is I will just create a comment here because it's also loading in the contour. So I'll just comment this. So next, what we are doing here is I need to be able to load this example. I'm just commenting all these things, so it's irrelevant. So next, what I'm doing here is this example.jpg. I'm loading this in a variable I0 and I'm converting it to this grayscale, and I'm also inverting the image so that wherever there is material deposition, that comes up as white, and where there is no material deposition, it comes up as dark. So I'm inverting it. So let me run this piece of code. Okay, I don't want any breaks here. Okay, so now I have this I0 variable. It contains the grayscale image and then the inverted image. Then I will quickly show you that how it looks like. Right, great. So this is the grayscale image, and again you can see that this is the toolpath which is followed. The toolpath is white and the rest of the regions are black. Having converted it into a grayscale image, which is this one, I believe. Yeah, I will open it outside MATLAB and I'll show you. So if it was this one, yeah. So this is the grayscale image which was generated by the MATLAB. Now I need to be able to systematically store its intensity values at every pixel. So what I have done is I have created this sweep line algorithm. So this is a sweep line. So what the sweep line is going to do is it's going to create a line at the top of this image, and along that line, the pixels that fall underneath, the intensity values will be recorded. So it will create a line on top of this image, and underneath that line, whatever pixel falls underneath that line, the intensity values of all those pixels will be recorded in a spreadsheet. So I created this code to actually show you that how it looks like. Let me see if I'm able to run it. The code is a little bit buggy. You need to spend a little bit more time on it to be able to run it. Anyways, I'll just try to show you. I think it should run. Yeah, I think it should run. Okay. I not. Okay, I don't need this I not. It is already grayscale, so I don't need to convert it to grayscale. Let me see if this part runs. Okay, this part is run. Okay, and then let's run this. Okay, this interleave function is not available. Let me see if I can find this interleave function. This interleave function, you can find it on the MathWorks forum. I will put in the appropriate links. Let me put an interleave function. Okay, will it run now? Yeah, it runs now. Okay, so you can see this line. This line is moving downwards, and as this line is moving downwards, you can see that the intensity plot is coming. I hope it is clear to you. In fact, what I should do is I should I should run an example. Let's say I will take this. So I think this would be much more clearer. So instead of example 2, I'll do 22 here. Yeah, see. Yeah, okay. So what you're seeing here is actually you see this sweep line. All the pixels that are underneath this sweep line are being plotted here. Now try to, I'll run it again. So you see how the pixel intensity is changing. So over here they were the black pixels, then white, and you can see that here are the black pixels, then white. So all the pixel intensity values are coming here. So if I draw a straight line here, wherever the pixel intensity is here in this particular region will have a higher value, and in the darker regions it will have a lower value. I hope I'm making sense. So once I know that how the pixel intensity values are stored using the sweep line algorithm, what I'm going to do is I'm going to export the pixel intensity values in a spreadsheet. So for that, you can see it's almost the same code, but instead I'm taking this variable m in 10 and I'm saving the pixel intensity values. I think I'll run this code from the top. Yes, it's run, and you can see this m intent variable. So ignore this nan. You can just simply delete these rows, this first row in the first column. These are the pixel intensity values for the sweep line which was on top. Yep. And you can see some are 5, some are 1, because this is not now an image. So what I will do is, of course, you can automate this, but I just wanted to quickly write this without any. So I wrote this without any thought for automation. Of course, you can create a GUI out of this also, but again, I have just done it quickly so that I can explain the algorithm. So this variable, I'm just copying this entire values and I'm pasting it here, and I'm going to delete these rows here in this spreadsheet, and I'll save this in this particular folder. I'll go save as, browse. Let me just save this as intensity. Okay. So now I have saved this as intensity. So next what I'm doing is, I'll just comment this part out because it is trying to load in the contour. We don't need the contour. Okay, so now what I'm doing is I'm taking this XLS read function, and it is reading this particular so I'll just delete this. It has to read this Excel sheet, is intensity. So under this variable name intensity, I am reading this spreadsheet. Then I have to adjust the orientation such that it appears the way the material is going to be deposited. So these are all transformations. So flip and then transpose of these intensities. So these are all done so that the orientation is correct. And then I will just simply show you this particular section. I'm just running this particular section, so from here to here, and you can see that using this image sc command, I am getting this toolpath values, and already you can see that this legend, from legend, this you can see that wherever this blue region, it has the 0 intensity, and then we have the highest intensity here. We have the highest intensity here. Now I need to create a function that can create a window, create a particular window, look at the pixel intensity values within that window, and give me the average. Create a window, look at all the pixel intensity values, and give me the average. So that is done in this block mean function over here. So I will show you that how this block mean function works. So let's say let's create a matrix. Let's say I'm going to create an Excel matrix. For example, I'm just creating a matrix E, and it has these values 1, 2, and 3. 2, 3, 4, 5, 6, 4, 5, 6, 7, 8, and 9. Let's do one more row. 10, 11, and 12. So let me just run it. Okay, so now this is the matrix. What I'm going to do next is I will take this function, okay, and I will take it as new, and instead of this intensity value, I'll just put this E. So this is the input of this function, and I want to create a window where let's create a window of 3 and 2 elements. So I will just quickly run and show you what it looks like. Okay, so let me look at this n value. So you can see that this n value is equal to 4.5. Now where did it get this n value from? I will just, so n value is 4.5. Where did it get this n value from? So you can see that I have specified that 3 and 2. So if I sum 1 plus 2 plus 4 plus 5 plus 7 plus 8, so that is 3 rows and 2 columns, and take the average over this particular window, you will find that it will be equal to 4.5. So what this argument did was it took 3 rows, and what this argument did was it took 2 columns. So the window happens to be 3 down and 2 across. So all these elements are now replaced by this particular value, 4.5. Right? So this is what I was trying to explain here also. So that all the elements which are in here must be replaced, and it will have this average value. So that is what is being done here. So forget about this this particular section. This is actually again trying to load in the contour dimensions. So this was difficult to, I'll just comment this out, comment out this entire section, and I'll run this particular code, and you can see. Now for the window which is 15 pixels high, 15 pixels, remember this is rows, so 15 pixels down and 16 across, this is the gradient of the toolpath. So now what you can do is you can just play around with these numbers, and you can see that as I play around with these numbers, how the sharpness in the gradient gradient disappears or it becomes even more sharper. And from there you can see that over what domain do you think, uh, do I think that my gradient is valid? Over what domain, over what region I will still be able to get the gradient in the toolpath. So this is 15 comma 16, you have already seen it. If I reduce it to, let's say, 10 comma, let me close it. If I reduce it to, let's say, 10 comma 11, what will I get? You can see the gradient becomes even more sharper, even more sharper. If I go on the other end, so let's say this is 50 comma 51, you will see that the gradient will become much more diminished. So you can see it is becoming much more diminished, and you can see still you can have some hint of the toolpath. But if I go even higher, let's say 100, 101, 100 and then 101, I am expecting that you can no longer make out the toolpath. Yeah, you can no longer make out the toolpaths. But you can see that over this particular region, because I'm now taking the averaged value, you can see the smoothness in the toolpath. You can see the smoothness in the plot. So this session got a little longer than I expected it to be, but nonetheless, I hope I made some sense here. You can take this code. Of course, you will have to fix some of the bugs in this code, and you can test this out for yourself. All right, thank you.